I want to put together a video today to introduce you to the idea of linearization, all right? Now, we're not going to get into everything that we can do with linearization today. All I want to do is get you used to the idea that we can take a graph that is not a linear graph and we can make it linear by making some adjustments. And that's what we're hoping to do here, all right? Now, to introduce us to this idea, this is a mathematical tool that we can use in physics. And in any science, when we're trying to determine relationships or trying to prove relationships. In this course, regular physics course or an AP physics course, we're probably going to see 4 different types of graphs. All right. As you get deeper into physics, you may see other types of graphs, but we're going to see 4 main ones here. All right. We're going to see some linear graphs. All right. Now, in a linear graph, we don't have to do anything. It's already linear. Right? The nice thing about a linear graph is it has a nice y-intercept, has a nice slope. Those things are usually representative of different things. And you've seen that before. When we had a position versus time graph, the slope was the velocity, right? When we had a velocity versus time graph, the slope was the acceleration. So you've seen it already that these things can mean, the slope can mean something. And so that's one of the reasons why it's nice for us to get a graph so that it's linear and has a nice constant slope. All right. The second graph you're likely to see is a quadratic graph. All right. So it'll be a nice curve like that. Now, I didn't put the left-hand side of the graph here, right? It would kind of scoop up like that. But very often, the graphs that we see will only be the right-hand side of the graph, showing how as x changes, y is not linear, y increases a little bit more rapidly than x does because y is proportional to x squared. Which means that every time x increases by a certain amount, that's going to end up being squared, and y will have a significantly larger change than x for that amount of time. We'll see that. You've seen that already, right? We know that, for example, position and time have a quadratic relationship when there's a constant acceleration. When you take an object and you drop it, it speeds up. The velocity is not constant. The velocity gets more and more and more fast as time progresses, right? It speeds up. That's what we're seeing here, a sharper and sharper slope. That's a very common type of graph that we'll see in physics. Now, right? So in both of these situations, as x got bigger, y also got bigger. But another type of relationship that we see quite often is an inverse graph. All right? Now, in this graph, you can see that as x gets bigger and bigger and bigger, the graph gets lower and lower and lower. Y decreases. They have an inverse relationship, right? You'll see this in a lot of different situations as well, all right? Notice that y then is proportional to 1 over x. That is the mathematical relationship we will use for an inverse relationship, okay? The last one is very similar to this. It's something called inverse squared. Now, you may look at that and you may say, Mr. Bawada, you just do the same thing, Mr. Bawada, same thing. Well, more or less. However, you can see that this one's a little bit steeper and it flattens out a little bit better than this guy does. Now, when you're just looking at it in a picture, it might be hard to tell. It might be hard to see which is which. And so that's one of the reasons, these two are one of the reasons why it's so important for us to learn this linearization process. Because if we try the linearization process and don't get a linear graph, then it's not the relationship that we thought it was. So that's going to be really important as we go forward here in just a minute. Okay, so you want to be comfortable with these 4 graphs. Linear, you don't have to do anything to. Quadratic has a relationship y versus x squared, okay, proportional to x squared, which means that we're going to square all the x values. An inverse graph is y is proportional to 1 over x, so we're going to do 1 over x for all the x values. And inverse squared will change all the x values by 1 over x squared. And I know some of you are like, oh, what do you mean by change the x values? I'll show you just in a second. We're going to go ahead and erase this. We'll put an example up here, and we'll try to walk through the process. All right, let's go. All right, so here's our first example. All right, we've got data being gathered for a child's toy that is slowly accelerating down a ramp, or maybe it's on a flat surface like one of those little cars that speeds up slowly. Okay, they measure the distance traveled by the toy in centimeters after a whole number of seconds. The data is shown in the table below. So we've got our time, we've got our distance. All right. So the first thing is determine which variable is independent and which is dependent. Well, the independent is the one that we are kind of in control of, and then the dependent is what's changing as a result. And so we're measuring for a whole number seconds, so that's going to be our independent. And then the dependent is going to be the distance, because the distance is changing based off of how much time we measure. All right. Number 2 says label the graph axes accordingly with labels and include units. So we're going to put a graph on here, okay? And hopefully this is going to be big enough for y'all to see. We got that. We'll put time in seconds over here, and we'll put distance in centimeters on this axis, okay? Make sure you use values such that you'll use most of the graph. So when we graph, we want to make sure that for time, we get all the way from 0 up to 5, and we want to use most of the graph. So I'm going to split this up into 1, 2, 3, 4, 5, and then I could have 6 if I needed it. That's more or less the right idea. And then for this distance right here, I've got 1, 2, 3, 4, 5, 6, 7 bars, but it only needs to go up to 19. So maybe I'll go by 3s. 3, 6, 9, 12, 15, 18. And so that's these marks right here. Just like that. Okay. And so we've done that. We've got the values. We've got the graph. Now it says graph the data. So we'll go ahead and put those data points on there. So we're going to put on 0, 0. We'll go ahead and put on the points. Done. All right. So now when we look at that, right, the next thing is identify the function type. We look at these points. It doesn't look like a straight line. Okay. If we were to draw a best fit line, it would probably look something like this. Now, I'm not going to zigzag. You don't do any zigzags when you do a best fit line. You try to do one smooth line. It can either be a smooth curve or it can be a smooth straight line. Okay, but we're not going to do zigzags and try to connect all the points. That's not what we're trying to do. We want to try to have one nice smooth line that connects everything. If it doesn't go through all the points, it doesn't go through all the points. Get over it. Okay, so you can see that one of the points is a little above, that one's a little bit below. That's fine. So we kind of fit all the points. Identify the function type. Well, that to me looks like the right-hand side of a quadratic. When you look at the 4 types of graphs, hopefully look back at your notes and look at those 4 types of graph that we talked about before this, and you'll notice that out of those 4, this looks mostly like that quadratic graph, where it looks like that right-hand side of the parabola, and that's hopefully what it is. Okay? We drew the line of best fit already. That's a smooth curve. Number 7 is linearize the data by changing the values on the x-axis appropriately. Now, you may remember for quadratic, what we wrote underneath the quadratic graph is we wrote this. Y was proportional to x squared. So what we're going to do is we're going to linearize now. And to linearize, what we're going to do is we're going to take all the x's and we're going to square them. And we're going to put that on the x-axis instead of 1, 2, 3, 4, 5 for time. Now, don't you dare just go on and change this to 1, 4, 9, 16, and 25 because they're not the right space apart. That's an important part of this process. So I'm going to erase what I got here. Okay, I'll leave the y-axis here because that can stay the same. But I'm going to change my x-axis. I'm going to actually square. We're going to take each of our x values and we're going to square them. So 0 squared. So I'm going to create a new kind of column here for time squared. So 0 squared is 0, 1, 4, 9, 16, and 25. So now I need to be able to go up to 25 on the x-axis. So let's go ahead and make some changes to our graph. All right, so you can see I squared all my times. We did that before. I changed the x-axis so it would fit everything from 0 up to 25. I went by 5s, and then I put the points on there. This is the x value. The t squared is the x value. It's time squared. And then the y value is still just my y values here. And when I put that into my graph, you can see I get a nice straight line. Now, what we can get from that, we're not going to worry too much about right now, other than the fact that we got a nice straight line, which means that the original data, the time and distance, have a quadratic relationship. We thought it was quadratic based off of the shape of the graph. This verifies it. It confirms that belief. Okay? So we linearized it. Describe how your analysis supports the function type identified in number 5. Well, because we said we thought it was quadratic, because doing y versus x squared gave us a straight line, that means it is quadratic. That's what we're saying for number 8. And then number 9, find the slope of the linearized graph. You should be able to get a slope here. I'm going to use 2 points. I'm going to use this point 2519. That looks like it's right on the graph. Don't use points that are off a little bit. Try to use points that are on the graph, okay? And ones that are right on a grid line, right? Don't make it hard on yourself. So I'm going to use 2519 and 0, 0. The other thing is don't choose 2 points that are too close to each other. Points that are farther apart are going to give you better information than points that are close together. Okay, so we'll use that. We'll go y2 minus y1, which would be 19 minus 0 over x2 minus x1, 25 minus 0, and we get a final answer of 19 over 25, which I can change that into a decimal if I wanted. I don't really want to, so that's my slope. Find the slope. And the last thing is write an equation for the linearized graph and hence the original data. So 2 things here. Original for the linearized graph and then the original data. So I'm going to write an equation in y equals mx plus b form. Okay? The y is going to be my distance here. Okay? So it's going to be distance equals the slope, which is 19 over 25, x plus b, which my y-intercept here is 0. So plus 0. Now what it means when it says hence the original data is it wants you to put back the things that you had before. So instead of having y equals 19 or 25x plus 0, it wants you to put back in that data. What was y? Y was the distance. So we're going to say distance is equal to 19 over 25. Now x, what is x here? X is time squared. And so we're going to put time squared in there. And then plus 0, just like that. And so now we have an equation relating distance and time, which is a quadratic equation. And that quadratic equation came from our use of linearization. We don't have to figure out the stretch and the squish and all those fancy things you learn about in math class. We can just find a linear graph and match it up by finding the slope. It's kind of a neat thing that we can do with this linearization process. All right? So that answers question number 10. All right, I'm going to erase it. We're going to try one more question.
All right, guys, here's the next question. This would be a little bit different, but we're going to follow basically the same process. All right, so we've got our situation again. We've got Elon Musk wants to verify the force of gravity at various heights. So he sends an astronaut up in a SpaceX rocket, and they run some tests. Okay, at various points in her trip, she measures the force of gravity and records her distance from the Earth. She knows that, as far as we know, that it actually doesn't depend on the distance from the surface, but the distance from the center. So she does some calculations so that she can convert her height above the surface of the Earth to the distance from the center of the Earth. All right, and she records the data in a nice little table on my whiteboard. Imagine, of all places to record her data. So here we go. We've got our data. The distance is in meters, but you'll notice that it's 10 to the 6th, so that's 1,000,000 meters. And you may say, well, that's a lot of meters. Well, yeah, it is a lot of meters, but that's also, we're getting up into the range of some satellites, right? And so it's actually not really that big on a big picture scheme, all right? So these are reasonable heights here, distances from the center of the Earth, all right? She also records the forces. We can see that here in the SI unit of newtons. All right, so we're going to go through the same process that we did before. And the first thing we're going to do is we're going to determine the dependent and independent variables. The independent, remember, is just the variable that she is recording first or that she has control over. That is going to be the distance, because when she gets to a specific distance, that's when she records the force. And the force is going to depend on what distance she decides that she's going to measure data at. So we've got independent for the distance and dependent for the force. All right, so now we'll go ahead and look at question number 2, which says label the axes and graph the data. And so that's what we're going to do. We're going to go ahead and put up a graph. I'll put the whole thing up, and then we'll talk through the decisions that I made. All right, here we go. All right, so you can see the graph that we got here. I decided on my axes, the distances, the numbers here, based off of what I needed, right? I saw that I had about 7 or 8 marks down here on the bottom, and I knew that the bottom, that distance, needed to go all the way up to 35, and so I decided to go by 5s. You could go by something else if you have more or less space there. The whole goal is to use more or less the whole graph, all right? And you'll notice that when we change our graph in a minute, I'm going to leave the markings there because the graph would already be there, but I'll change the scale based off of what the data is. The y-axis here, again, I looked at the values that needed to go basically from about 0 up to 10, and then I made sure that I had enough markings to cover those. Once I did that, I just plotted the points. Of course, part of labeling and drawing the graph is number 3, where we want to now draw the line of best fit and identify the type of graph. And so at this point, we're going to go ahead and draw in a line of best fit. And remember, line of best fit doesn't mean, like in geometry, just a straight line. It could be any curve of best fit. And so this obviously is not a straight line. It is more or less kind of a curve. So we're going to draw that in. Oops. And we've drawn in our curve as best we can. You can see that my purpose was trying to make a nice smooth curve. I'm not just connecting all the dots, I'm drawing a nice smooth curve. Nature tries to be simple. Nature isn't going to have a lot of different lines and different slopes and things like that. It's either going to have a continuously changing slope with a very smooth curve, or it's just going to be a straight line. Nature likes to be simple. That's just the reality. It follows laws, and laws can be resembled, generally speaking, with simple mathematical formulas. All right? So, we've got our line, and we say, well, we look at that, and we say, well, it doesn't really look, well, it's definitely not linear. It doesn't really look like a quadratic, right? You might say, well, maybe it's a wide quadratic. And if you think through the situation, a quadratic wouldn't really make sense here, right? A quadratic would mean as we get further and further away from the Earth, that the force of gravity would start getting stronger again. And we know that that doesn't really make sense. So we're going to kind of nix quadratic number 1 just because it looks a little too flat down here. And number 2, because our understanding of physics says that wouldn't really make sense. All right? So we're down to either it is inverse, which means it would be 1 over x, or it's inverse squared, which would be 1 over x squared. Now at this point, you probably don't know. Okay? At some point, you may be able to look at that and say, well, it looks a little more like this. Or I know the physics and I think it should be this. But at this point, we don't know that. So what we're going to do is we're going to try an inverse graph. We're going to try that first. So inverse, remember, is y is proportional to 1 over x. What that means is we're going to take each of our x values over here in our distance column, and we're going to do 1 over x. And then we're going to graph it. All right? So I'm going to do all that right now. All I'm going to do over here in my table is I'm going to create a new column, and I'm going to do 1 over 6.5, 1 over 11.6, 1 over 16. And I'm going to get some numbers, and then I'm going to redraw my graph. The y values are going to stay exactly the same way that they are, but my x values are going to be that 1 over x values instead of just x. We're going to see what the inverse graph looks like. All right? Here we go. All right, what do you see? You saw we did the calculations of the 1 over x, and we got some numbers there. Notice I rounded to 3 decimal places. You don't really need more than that. You're not going to be more precise than that on this graph anyway. Let's be honest, right? So I just wrote 3 decimal places. I then decided what to put on my x-axis. You may have noticed that I actually was going by 0.3s, and then I got to the end and I realized that I had a bunch of empty space at the end because I got up to like 0.18 or 0.21 or something, and I said, my data only goes up to 0.15. Maybe I can go by 0.02 instead. And so I changed it and I went by 0.02s. That's fine, right? But you want to make sure that you're using a good part of the graph so that you can see things a little bit more clearly. It'll help you determine whether a graph is linear or not. All right, so we now have our graph here. What do you think? What does it look like? You may say, well, yeah, that looks a little bit better. If I were to draw a straight line in there, would it fit the data? Would it fit what the data is trying to tell me? Look at this. Do you think that that is the best model for these blue points? I hope that you're sitting there saying, no, Mr. Bauer, you messed up. No, I didn't I messed up. I chose the wrong relationship, right? If you do the linearization process and you get a graph that is clearly not linear, right? If I see these data points, I'm not going to draw a straight line in there. I'm going to draw a graph that looks like this, which is not linear. Notice it doesn't necessarily go through all the points. It just has to be close to them. That's a much better fit, right? That's a one simple smooth curve, and yet that is a significantly better fit than that green line that I drew. All right, so what I want you to recognize is that if it doesn't give you a linear graph, then it is definitely not an inverse relationship between distance and force. Now, what do? Well, if we have another option, let's try another option. We'll try something else, right? The original data we already said wasn't linear or quadratic. We couldn't decide between inverse and inverse squared. We tried the inverse, it's not working. So maybe what we should have done was inverse squared. All right? And so that's what we're going to do now. We're going to go through and do it one more time. But this time, instead of putting 1 over x here, we're going to do 1 over x squared. So I'm going to do 1 over 6.5 squared. 1 over 11.6 squared, 1 over 16 squared. I'm going to do that all the way down, and again, I'm going to change my axis, and I'm going to redraw the graph, and fingers crossed, hopefully this time, we get a linear graph. All right? Let's go. All right, so we've got our data points up here, right? We did the 1 over x squared to do our inverse squared, and so we just took each of those x values like we said before, and I calculated each of those. Notice that the numbers are decimals. You can change that if you want. You can multiply everything by 10,000 and just make a note of that down here that you made some changes, or you can just deal with it. I decided just to deal with it, so I went 0.0003. 0.003, 0.006, 0.009, just to make sure that I could fit all of my data points on there. I then graphed the data points, right? And we can see the data points here. And this time, look at this. It's not perfect by any means, but that's a pretty good graph there, right? It's not bad at all. Now, it is off just a little bit, right? We do have a little bit of a bend there, but, you know, it's so close to that linear graph, it's much better than any of the other graphs that we've seen. So what this would kind of warrant us saying, hey, it looks mostly like inverse squared if we're assuming that it's kind of a simpler function here. Let's go gather some more data, send up another rocket, right, and see if we can verify this. This straight line verifies or shows us that the relationship between distance and time, distance and force is 1 over x squared. All right. Notice that I did change my units down here. It's now 1 over distance squared. I did the same thing on the previous graph as well, but I didn't mention that. But we do have 1 over distance squared now. The units are 1 over meters squared. So we can now then create a equation, right? We can find a slope. We can get a y-intercept, which hopefully is 0, 0. If we've done the linearization correct, most of the time we should get a intercept of 0, 0 there. All right, so here we go. We're going to try to come up with an equation. We need a slope. We definitely need 2 points on the line. I'm going to take 0, 0 as one of them. It doesn't matter that it's not one of the data points. What matters is that it's on my line. And then you want to make sure to choose another point that's pretty far away. Please don't choose a point down here because those 2 points are too close together. The uncertainty, when you draw 2 points that are close together, it's too likely that your slope could be off by just a little bit. And when you're off by just a little bit in a small distance, it ends up being off by a lot. Think about if you were 1 degree off as you were walking towards a person, right? You're 1 degree off, you're probably not going to be off by very far. But what if you're 1 degree off, that same angle, and you go out to the moon? The farther and further you get out, the farther you are off. And that 1 degree is going to be a problem going to the moon. Whereas going to visit a person, that's not really a big deal. All right, so hopefully that kind of makes sense. Don't pick points that are close together. Pick points that are far apart so that any uncertainty there is less significant. All right, so we'll go ahead. I'm going to go ahead and take this point right here. It's pretty much on the line. If I had a better grid line on here, I'd try to choose one where it's much easier to read, but these are all estimates anyway. So we're going to go this point right here. Which was 0.0237, 9.8. And so we will go y2 minus y1, because my other point, remember, is 0, 0. And then x2 minus x1. And that's going to give me my slope. We punch it into our calculator here. And we get 413.5. So I'm just going to go with 413 is my slope. So now I should be able to go y equals mx plus b. So it'll be y equals 413x. But, so this is this equation for the linearized graph, but we want it for the original data. Right now it's just y and x. So for y, I'm going to put in the force. So I'm going to say the force is equal to 413, and then x is going to be 1 over the distance squared, because that's what is on my x-axis there. So 1 over distance squared, and we'll just need to note that the distance should be in 10 to the 6th meters, and if you put that in 10 to the 6th meters, the units will all work out so that my force, my final force, is in newtons. And so there we've shown you what it looks like if we choose the wrong function. And remember that that tells you something too. If you use the wrong function and don't get a linear graph, then that shows us that function was wrong. That's just as important sometimes as knowing that the function is right. Okay, so keep that in mind. We also showed that the inverse squared is the correct relationship because we ended up with a fairly straight line here, one that's pretty good. All right, hopefully that was helpful. Go ahead and see if you can use all of that on your work.